Hello, this is lecture 20B of Differential Equations and Linear Algebra. Very soon, like the next lecture or two, we're going to start getting into applications of the abstract vector space theory that we've been talking about to both differential equations and difference equations. The differential equations in the lecture A's and the difference equations in the lecture B's for the most part, but we'll talk about both in both parts as well. 20B, I review some things, dimension of a vector space. Also down here, change of basis or change of coordinates in Euclidean space. But I've got some other things that need to come into play. Something called the rank theorem, also known as the Rank-Nullity theorem, the invertible matrix theorem, and applying change of basis or change of coordinates, not just to Euclidean space Rn, but to any finite dimensional vector space. Okay, so start with a review again of dimension. What is the dimension of a vector space? We can use coordinate vectors to help us define the dimension. Let V be a vector space with a finite basis, with n vectors in it. Then you can say that any set with more than n vectors must be linearly dependent. That's the first thing. Second, any set in V with fewer than n vectors cannot span the vector space. And thirdly, every basis of V must in fact consist of exactly n vectors. Okay? This makes good intuitive sense when you think about column vectors in Rn, but it's true in any finite dimensional vector space. The dimension is going to be the number of elements in the basis, which by 3 is the same no matter what the basis is. And again, as long as the vector space is not just the trivial vector, it's going to have infinitely many different bases. Bases is the plural of basis. This leads to a definition. If V is spanned by a finite set, then V is said to be finite dimensional. And the dimension of V, written dim V, equals the number of vectors in any basis for V. Because of the theorem, that's going to be the same no matter what. So it makes sense as a definition. Again, the trivial vector space, just the zero vector, has no basis. We define its dimension to be 0, which makes sense. It's just a point. It's zero dimensional. And finally, and this does happen, if V is not spanned by any finite set, then V is said to be infinite dimensional. Okay, and function spaces quite often are infinite dimensional, like C of AB, we've talked about that. Function spaces that solve differential equations are not infinite dimensional. You may want to think about that based on what I've said in the past. Here's the theorem. Let H be a subspace of a finite dimensional vector space. Then any linearly independent set in H can be expanded to a basis of H, that subspace. And furthermore, this makes sense, the dimension of H must be less than or equal to the dimension of V. And in fact, you could say if H is a subspace that doesn't equal V, you can put a strict inequality there. The dimension of H would be strictly less than the dimension of V. And we have something called the basis theorem. If V is n-dimensional, with dimension greater than or equal to 1, so V is not the trivial vector space, this is very nice. This is very useful, this basis theorem. Any linearly independent set of exactly n elements in V automatically is a basis. In other words, it automatically spans V. So it's a basis for V. And secondly, any set of exactly n elements that spans V also is automatically a basis for V. It will automatically be linearly independent. Very, very useful to only have to check one of those things once you know the dimension of the vector space. And that, in fact, is useful for differential equations and difference equations. There's something called the rank theorem, which I've hinted at with our examples, but haven't really written down precisely. Before we can state the rank theorem, we need some other definitions. Let A be an m by n matrix. So m rows, n columns. Keep a picture in mind. A is some arbitrary matrix with m rows and n columns. You know, the rows go across, you're counting the number of rows, there's m of them. The columns go up and down, you're counting across, there are n of them. It's going to be important to keep in mind here. Each row of A can be identified with a vector in Rn. Each row. We've talked about column vectors plenty. We haven't really talked about row vectors. but each row has n entries because there's n columns. You could think of it as a vector in Rn. But wait a minute, shouldn't it be a column vector if it's going to be in Rn? Well, essentially the set of all row vectors as a vector space with n components is isomorphic to the set of all column vectors with n components. You can think of it in terms of isomorphism if you want. If you want to be more precise, the linear transformation that maps this row vector to the corresponding column vector, well, it will be a linear transformation, it will be one-to-one, it will be onto. It's an isomorphism. So yeah, we can certainly think of row vectors as being in Rn as well. The span of the rows of A is called the row space of A. How about that? Row space of A. We have column space of A. We don't want to give short shrift to the row space of A. The set of all linear combinations of those rows. You could also call it the span of the rows, like I did here. That's called the row space. The span of the columns, set of all linear combinations of the columns is the column space. The row space is the set of all linear combinations of the rows. And if m and n are different, the column space and the row space don't even live in the same universe, so to speak. One's, if you're talking about the row space that have n entries in them, that's going to be some subspace of Rn. And the column space, since they have m components, m entries, is going to be some subspace of Rm. Let AT, we've seen this notation before. T is not a number. It's just a symbol that represents, take the transpose of A. Is an n by m matrix. A itself was m by n. The transpose is n by m, where each row of A has become the corresponding column of A transpose. A transpose sort of made this look like it has more columns than rows, would then, if that's the case, have more rows than columns. It's going to be n rows and m columns. And if, for example, the 17th row consists of 1, 2, etc. through n, just to pick something. If the 17th row of A is that row vector, then the 17th column of A transpose will be that column vector. You swap. You take each row and make it a column of the transpose. The first row becomes the first column, the second row becomes the second column, the third row becomes the third column, etc. That's what the transpose is. With a little bit of thought, you realize the row space of A is essentially the same thing as the column space of A transpose, as long as you ignore the fact that the row space of A consists of row vectors and the column space of A transpose consists of column vectors. They're isomorphic to each other. Okay? So we can think of row of A as being the same as the column space of A transpose. Here's a theorem that is sometimes useful if we want to focus on finding a basis for the row space. If two matrices are row equivalent, in other words, you can get from one to the other by doing row operations, then their row spaces are the same. Okay, so row operations don't affect the row space. Furthermore, if B is an echelon form, or reduced row echelon form for that matter, then the non-zero rows of B, the ones with the pivot position, form a basis for the row space of A as well as the row space of B. That's kind of nice. Just get to your RREF, say, look at the rows that are non-zero. Those will be a row space of the reduced matrix, but also the original matrix. Doesn't happen that way with column spaces. Okay, you might remember what we said about that. Here's a definition. The rank of A is the dimension of the column space of A. And we can write rank of A equals dim of column of A. That's a definition of rank. And now we have something called the rank theorem, also known as the Rank-Nullity theorem, this one right here. Let A be an m by n matrix, just like we had at the start. M rows, n columns. Then the rank of A not only equals the dimension of the column space, but it's also the dimension of the row space. They have the same dimension. They're subspaces of different vector spaces. Again, row space being a subspace of Rn, column space being a subspace of Rm. But their dimensions, the number of elements in any basis, are the same. The conclusion is essentially that the dimension of the row space of A is the same as the dimension of the column space of A. That's what this is saying. This was a definition here. This is a theorem that needs proof there. This also equals the number of pivot positions in A. And for a final conclusion, the rank of A plus the dimension of the null space of A equals n, the number of columns of the original matrix. This is also written as rank of A plus nullity of A equals n. The nullity of A is the same by definition as the dimension of the null space of A. Okay? I'm not going to take the time for examples because we have other things to do in this lecture. I would encourage you to consider some examples, do some row operations, and see that this works. Okay? And if you think about pivot positions and free variables, it even makes a lot of sense why it should work. Maybe we'll do some examples in lecture 21b. Continuing, though, in other facts and definitions that are important, let A be an m by n matrix. We can define something called the 4 fundamental subspaces associated with A. Let's pretend, for the sake of drawing pictures, that A is 3 by 3. Say A is 3 by 3. So the resulting linear transformation defined by T of x equals A times x maps from R3 to itself. Just keep that in mind because we're going to just draw some pictures here. This is going to be R3 as a domain of T. And over here, this is going to be R3 as a codomain of T. T maps from one three-dimensional space to the other. Kind of weird to think about it that way, but that's one way you can think about it. One fundamental subspace, this is a definition, not a theorem, is the row space of A. And like I mentioned in the last slide, that's the same as the column space of A transpose. Second fundamental subspace is the null space of A. Third fundamental subspace is the column space of A, which is the same as the row space of the transpose. That should make sense. And finally, the fourth fundamental subspace is the null space of the transpose. By the relationship between matrix multiplication and dot products, all the vectors in the row space of A are orthogonal to all the vectors in the null space of A, and vice versa. A similar relationship holds between the column space of A, which is the row space of A transpose, and the null space of A transpose. Well, why does this work, first of all? Why does this make sense? Think about it. If this is A, and you've got a vector x in the null space of A, say it's ABC, it's going to get mapped to the 0 vector. And because we can think of matrix multiplication in terms of dot products, in other words, the first entry of the output is the dot product of this row vector with x. The second row of the matrix dotted with this vector gives you the second component of the answer. And the third row of A dotted with this vector gives you the third component. All those dot products are 0. And therefore, this vector in the null space is orthogonal to each of these three vectors in the row space of A. And what that means is if, for example, the null space of A is a one-dimensional line through the origin in three-dimensional space, the row space of A can be thought of as a plane to the origin perpendicular to that line. They intersect at a right angle here. Okay, you gotta use your imagination. The line is going into the board that way. The plane is kind of like this. The intersection, this is supposed to be a right angle here, is what this is showing. That's the row space of A. And a similar kind of picture can be drawn relating the null space of A transpose to the column space of A. If the null space of A is one-dimensional, the column space of A, the image of T, will be two-dimensional. Maybe it's a plane that looks about like this. That might be the column space of A. The null space of the transpose is going to be orthogonal to that, perpendicular to it. Vectors in these spaces are orthogonal to each other. Now, it is possible for these spaces to be trivial, just the zero vectors. In which case, for example, if the null space of A is trivial, then the row space of A is going to be all of R3 in this case. Bringing this up just for completion, we will see some applications of it later. Another important theorem is the invertible matrix theorem. This is just part of what can be said. You can say even more than what I have here. Let A be an n by n, in other words, square matrix. Then the following statements are equivalent to A being invertible. I'm going to have a list of statements here. They're all equivalent to the condition of A being invertible, which I also call non-singular. Non-singular means invertible. Singular means not invertible. I know that's confusing, but I mentioned why earlier. Essentially, singular is a rare thing. Non-invertibility of a square matrix is a rare thing. If you make the entries of the matrix random, in all likelihood, it will be invertible. It will be non-singular, not rare. The determinant of A is non-zero. That's one condition of being equivalent to being invertible. We already knew that, actually. Secondly, the columns of A are linearly independent. A is a square matrix here. N rows, n columns. Same number of rows, same number of columns. And you can also say the columns of A span Rn. This is really the basis theorem that would guarantee these are equivalent. That these two things are equivalent, at least, to each other. Rn is n-dimensional. Having columns that are linearly independent mean they're automatically going to span, and vice versa. And will automatically be a basis for Rn. The column space is all of Rn, and in fact those columns form a basis for Rn. The dimension of the column space, the rank of A, is n. The rank is full, you might say. It's as big as it can be. A is n by n. And the flip side, the nullity is as small as it can be. The null space is just the zero vector. The nullity of A is the number 0. The dimension of the null space is 0. Okay, so haven't really talked about this much, but we will make use of it from now on, from time to time. Is it something you should memorize? Well, I don't know that you need to memorize it word for word, but it should sort of be in your soul. It should be something you automatically think about when you're thinking about square matrices and whether they're invertible or not. You've got different ways of seeing whether they are and characterizing them. All right, our last couple slides are about change of coordinates. I did introduce this in lecture 19b. We'll be thinking about it in Euclidean space Rn, but we'll also be thinking about it in a general vector space. The notation gets kind of unpleasant, you might say. It's easy to get confused. Just keep your wits about you. Keep the main ideas in mind as we go. Let B, which is B, vectors b1 through bn, be an ordered basis for Rn. Remember, it's the context of ordered bases that we have coordinate vectors in the coordinate mapping. We have to give our basis an order. Any order is okay, though some might be preferable to others. Theoretically, any ordering is okay, but you just have to pick some ordering. Let PB be the n by n matrix whose columns are b1 through bn. PB, I introduced this through an example last time, is a change of coordinates matrix. And in fact, I think this slide I showed in lecture 19b as well. PB is called the change of coordinates matrix from B, this basis of Rn, to this standard basis of Rn. E1 is 1, 0, 0, 0, 0, etc. through 0. E2 is 0, 1, 0, 0, 0, etc. E3 is 0, 0, 1, 0, 0, 0, etc. etc. En is all zeros and then a 1. Those are our standard coordinate vectors, standard basis for Rn. PB is called the change of coordinates matrix for this arbitrary ordered basis of Rn to the standard basis. What does this mean? Suppose x is on Rn. If the coordinate vector relative to B is this, notice I'm using the transpose because I really want to think of it as a column vector here, then this is true. The old coordinates, so to speak, for x, which are really with respect to the standard basis, can be found by taking this change of coordinates matrix, P sub B, this entire thing represents a matrix, times the coordinate vector of x relative to B. Why? Well, this is an ordered basis for Rn, so by the unique representation theorem, x is some linear combination of those b's, calling the weights C1 through Cn, these are unique. They, by definition, define the coordinate vector. The coordinate vector for x, this thing right here, is this vector right there. Technically speaking, as a column vector. That's what the coordinate vector is. If you multiply PB times that vector, you do get this linear combination by the definition of matrix times a vector that we talked about a while ago. This matrix times this vector is a linear combination of the columns of the matrix with the components of the vector as the corresponding weights. So PB transforms the coordinate vector of x into its regular form in terms of the standard basis. But you can go the other way around. The invertible matrix theorem can be applied to say that PB is invertible, and you can solve for the coordinate vector of x with respect to the basis B, the ordered basis, as the inverse matrix of P times x. Essentially just solving that equation for the coordinate vector of x relative to B. If this equation is true, I can multiply both sides by P inverse, which will exist by the invertible matrix theorem. And then the associative law holds here. So I can write this. And then these are inverse matrices. This is the n by n identity matrix, which when you multiply times any vector, you get the vector back. Okay, so you should be able to verify this doing the kind of calculations that I just showed you here. It's a little confusing. P transforms the new coordinates back to the old, so to speak. It's its inverse that transforms the old coordinates back to the new. Keep that in mind. That's very helpful to keep that in mind. More general change of basis between arbitrary vector spaces, or in fact a single vector space with two different bases is what we have here. It can be useful to be able to change between two bases of a given vector space, an abstract finite-dimensional vector space. This means we want to relate the corresponding coordinate vectors. Here's an abstract example. Is it possible to have an abstract example? Yeah, this is one case. Let V be an arbitrary vector space with dimension 2, just to keep things simple. V could be a space of functions. It could be the span of cosine of t and sine of t, for example, as a common basis we might use with differential equations, or the span of e to the 4t and e to the negative 3t is another common example we might use with differential equations. Suppose B is B1, comma B2, and C is another basis, C1, comma C2. Two ordered bases of B with the property that B1 is this linear combination of C1 and C2, and B2 is this linear combination of C1 and C2. Let X be this linear combination of B1 and B2, and find the coordinate vector of X with respect to C. I've got two bases here, B and C. I know the coordinate vector of X with respect to B. It would be, look at the coefficients, 1, 2. The column vector 1, 2. I want to find what this column vector is, the coordinate vector of X with respect to the basis C. How do you do it? You might want to pause and see if you can figure it out. Okay, back. Here's all the details. We can use the linearity of the coordinate mapping. Maybe you didn't think of that. The OP property, operation preserving property. X, the coordinate vector of X with respect to the basis C. Well, first of all, because X is this linear combination of B1 and B2, I can make this substitution. And then, yeah, the coordinate mapping is linear. I can break this apart into a linear combination. 1 times the coordinate vector of B1 with respect to C plus 2 times the coordinate vector of B2 with respect to C. And these equations here and here are going to help me find those coordinate vectors. This coordinate vector will be, look at these coefficients, 3, 2 as a column vector. And this coordinate vector as a column vector will be 2, negative 4. Plug those in. Simplify. You get this. And that's the answer. That's the coordinate vector of X with respect to the basis C when I know the coordinate vector of X with respect to the basis B, which is 1, 2. And lo and behold, we have yet another linear combination of some column vectors here. This can be thought of as a matrix times a vector. This matrix times this vector. Why? Because there we have a linear combination of these two columns, 3, 2, and 2, negative 4, columns of the matrix, with the weights 1 and 2 being the components of the vector that we multiply. If you multiply this out, you'll see that you get this. Try it. In abstract, what we have here, 3, 2, is the coordinate vector of B1 with respect to C, 3, 2. Second column, 2, negative 4, that's the coordinate vector of B2 with respect to C, 2, negative 4. And 1, 2, that is the coordinate vector of X relative to B. Look at the weights, 1, 2. This matrix has a special symbol. It's this weird symbol. This is one of the things that's hard to get used to, and it's easy to get confused. This entire symbol represents that matrix. It's the change of coordinate matrix from B back to C. And the reason we put a B over here and an arrow pointing to the left and a C over there is because the coordinate vector of X relative to B is over here on this side of the equation, and the coordinate vector of X relative to C is over here on this side of the equation. So if we're thinking in terms of new coordinates and old coordinates, it's really like this is the old coordinates and this is the new coordinates. The P matrices always transform new coordinates, or excuse me, yeah, I meant to say that, I forgot if I said it right. New coordinates right here to old coordinates. B is the basis for new coordinates, C is the basis for old coordinates. Of course, that notation is arbitrary. I could have switched the roles of B and C around. The general case when the dimension of V is n, and by the way, I re-emphasize this is an arbitrary vector space of dimension n here. Dimension 2 here, dimension n. We can still work with matrices in arbitrary vector spaces as long as they are finite dimensional. The change of coordinates matrix looks like this. This is the change of coordinates matrix from B to C. The columns are the coordinate vectors of the B basis, B ordered basis, relative to the C-ordered basis. A very similar kind of equation is going to hold. That you see in the line above it. The coordinates of x relative to the C-ordered basis, which you want to think of as old, typically, is this matrix times the coordinate vector of x relative to the new basis. Again, usually you want to think of C as the old basis in this notation and B as the new basis. But that also means you can solve for the new coordinates in terms of the old. You can multiply both sides on the left by the inverse of this matrix, which will exist. This will be an invertible matrix. I could write this. It's easy to get confused when you're writing these things down as well. And I guess that would mean, evidently, this inverse matrix of P must be the same as this, where I switch the B and the C around. That must be the case, because I am going back and forth between these coordinate systems. Okay? This is useful. We're going to see applications very soon. But it also is very confusing. So many symbols, so many ideas. Easy to get the B's and the C's mixed up. Weird notation, okay? Got to keep your wits about you. Let's go back to Rn, though. We feel that's the familiar vector space here. In Rn, if V is Rn, then the coordinate change matrix from B to the standard basis of Rn is the same as the matrix PB that we talked about earlier. The ordinary coordinate change in Rn that we talked about earlier. It's the same matrix. Here's a general algorithm for computing this change of coordinates matrix when V does equal Rn. Not going to take the time to explain this, but I will show how to implement the algorithm on Mathematica. You do some row reduction. You row reduce an augmented matrix. It's an n by 2n matrix with n rows and 2n columns. Double the number of columns than the number of rows. It's this matrix, and I wanted to make this line a dashed line, but my math typesetting didn't give that as an option. Usually with augmented matrices, I make dashed lines. Take the C vectors from the C basis, put them in the first n columns, and these are column vectors, and then take the B vectors from the B basis, ordered basis, put those in the next n columns. Do row operations to reduce row echelon form. If these truly are bases, you will be able to get it into this form. Again, pretend that's a dash line. And whatever n by n matrix over there, that's going to be that's going to be P. Let's end with an example, and then we'll show you Mathematica. When n is 2, we are thinking about R2 here. Here's the B basis. This is a basis, because, for example, these vectors are not scalar multiples of each other, so they're automatically linearly independent, and therefore, by the basis theorem, they're all automatically span as well. They are a basis for R2. Same kind of thing can be said about C. What is this matrix? Let's do the algorithm here. So I've got my augmented matrix here. Notice these are the C vectors, C1 and C2. C is right there. And these two are the B vectors, B1 and B2. And this example works out nicely to not bother with fractions. Here's the first step of the row reduction. You should take the time to check that. I guess I did 2 steps. I first multiplied row 1 by -1/4. And then I did a row replacement operation to get a 0 underneath that leading one. Multiply row 2 by 2, and then get a 0 up there. These next 2 steps. And there is the P matrix, the change of coordinates matrix from B back to C. It's this. And we can also find its inverse And that inverse matrix would be the coordinate change matrix from C back to B. There's the inverse, and I use the shortcut for the inverse of a 2 by 2 matrix here. Inverse of this matrix takes 1 over the determinant. The determinant is -2 because it's 18 minus 20. You swap the numbers on the main diagonal, the 6 and the 3 swap places, and you put negative signs in front of the numbers on the off diagonal, which makes them -4 there, -5 there. By the way, if one of those was negative to begin with, for example, if that was -4 to begin with, it would become +4. Negative of a negative is positive. Then multiply through by the -1/2, and you get this matrix. That would be the inverse of this matrix. Let's end with Mathematica. Illustrating the row operations and the answer. So the P matrix is this one right here. If I did the row operations the other way, if I didn't just invert this with the shortcut formula, but if I swap the columns here, notice -4, 2 goes there, -3, -1 goes there, the B's and C's are swapping, -9, 7 goes here, -7, 5 goes there. If I row reduce that matrix, oops, then this matrix is the other one. It's the inverse matrix of this one right here. -3 halves 2, 5 halves -3. That is the same as what was on the PowerPoint. Right here, -3 halves 2, 5 halves -3. Right, those are the same. Yes. Looks good. Okay? So again, you're not quite seeing the point of all this. The point is very soon to come. Next couple lectures, we're going to start getting into the application of all this theory. Thanks for watching.